distribution. You know that meteors are Poisson distributed, so the number of meteors that you see per time interval follows a Poisson distribution. In order to generate these artificial signals, you need to have the inverse. So I would have to need to calculate the inverse Poisson distribution. That's quite complicated, but you can use, that's a little hint for the mathematicians, you can use the exponential function. There it's fairly simple to get the inverse, and this allowed me to really now generate meteor data. This is how it will look like. I start with a constant signal. You see no periodic signal, just a constant signal. This is now my simulation. So I generated, based on this constant signal, some Poisson distributed numbers. These are like my meteor counts. Then I simply load this into MeteorFlux. So this is a flux density graph that I would see in MeteorFlux. And then I calculate the spectrum, which is a function of MeteorFlux. And you see, okay, as expected, just random. There's no peak in the frequency signal because there was just a constant input. So this is what we see here. There's no preferred frequency. Now let's try to play with the parameters. I take the same constant background. I add now some periodic signal, in this case with a wavelength of 90 minutes, with a strength which is a little weaker than the background, and see what happens. So again, this is here my generated, my Poisson distributed input signal. I load it into MeteorFlux, and this is a spectrogram that I get. I mean, this is fairly obvious. We have a nice oscillation here, and there's one big peak in the spectrogram at exactly 90 minutes wavelength, so works as designed. So let's play a little with the parameters. What I can change, for example, is to change the wavelengths. Going down, like from 90 minutes, you have a very short wavelengths in the region that we are waiting for, like 5 minutes. So you see it's not nice sine wave anymore because it's sampled just 5 times per sine. Also the Poisson distribution, which is generated, you hardly see any periodic signal any longer. I load this into MeteorFlux, again, looks like constant background, but if we do the frequency analysis, very nicely, we see this 5-minute wavelengths, so that works out. If I change the input frequency, it clearly also changes my spectrogram as expected. Let's go down further. What happens if I mix 2 frequencies? So I've taken here 2 frequencies, like 10 and 7 minutes. Also here, this is like the raw signal. I generate the Poisson distribution from it. You wouldn't see any periodicity. You load it into MeteorFlux, but then the spectrogram clearly shows 2 peaks, one at 7 minutes, one at 10 minutes. So which means that this FFT with this fixed bin size is also properly separating between different wavelengths if I have a mixture. So this is also positive. So what is if I change the bin size? So not using 1-minute bins, but using 3-minute bins, so averaging the data a little. Yes, of course, my frequency resolution is reducing, and also the SNR is getting a little worse, but still my main frequency or my main 2 frequency in this example, like with 10 minutes and 7 minutes, are still nicely visible. So also that it will hurt a little, but at least the main information, these 2 oscillating signals that I put in the beginning are still visible in the end. Okay, I can further reduce the strength of my signal. Of course, if I have less strength, I have less information, and I still see the main peak here. In this case, it was 7.5 minutes. I still see it, but the SNR is getting worse. And if I further reduce the signal, of course, at some time, it's more or less just noisier. So there has to be at least a certain signal strength to be able to detect the wavelengths. And the last thing that I tested is, now if I reduce my window, not observing here in this example case for 6 hours, but only for 2 hours, so I have less data, it looks the same, my distribution, also here it looks the same. In the end, my resolution is reducing and also the frequency range. But most important, again, my primary input wavelengths, which I used here in this analysis, is still nicely visible. So long story short, when I play with the parameters, it shows me exactly what I want to see. If I change the wavelength, I see it in the spectrogram. If I do the binning, it's reducing my resolution, but still my primary wavelength is visible in the spectrogram. And now I tried to simulate my Leonid observation, and that was really not like taking 4 hours optimizing. I just did taking some constant background, and I added like 2 periodic signals, one with a wavelength of a little more than 7 minutes, which we knew is mainly there in the data, and another one with something like 4 minutes. Again, generate a random distribution, load it into MeteorFlux. This is the spectrum that I get, and if we compare that with what I really saw from the 1999 Leonids, it looks quite comparable. So it's not obviously not exactly what we see, but with these 2 peaks here in my model, and again, it's not really that I was tweaking the parameters to get this model as good as possible. It was really just a quick shot. Hey, let's take these 2 frequencies, play a little with the weight, and that's it. But it gives me a spectrogram which looks quite similar to the Leonids 1999. From what I would conclude that indeed in this 1999 Leonids, we have an input signal which has some strong periodicity and which is also quite prominent in the signal. But really to now identify which of these frequencies these are exactly and how strong they are, that would require some more Monte Carlo simulation or something. For me, the lessons learned was, yes, Leonids 99, the periodicity is there for sure, and I can prove that if the binning is constant, if I put in a certain signal, I see it in the spectrogram. So I believe that these oscillations that we see in the Perseids, that they are real. Okay, I have like 2 or 3 more features that I implemented. One thing is based on a paper which Althea Moorhead is about to publish. What she has done, and this is like a little advertisement for the paper, it's really worthwhile reading. She has tried to combine flux density data from radar, from video, and from visual observations. And I don't want to repeat the full paper, but here 2 of the most important things that Althea came up with is, one thing is she has problems because the different teams were using different population indices for the same shower. Of course, that is bad because you're scaling the shower in a different manner, so that must be constant. And the second thing that she proposes, well, so far all the observations are reduced to a standard limiting magnitude of 6.5. Yes, we all know that. But her idea is, well, that's not good, because if you have radar like 8 or 9 magnitude, you are extrapolating over 3 magnitudes. Whereas on the other hand, if you have video with like 2nd or 3rd magnitude, again, you're extrapolating to 6.5 over 4 magnitudes. So you will introduce big errors. And her proposal actually is that we are not using first of all, everyone is using the same R value. Thank you. But second thing, that everyone is using not 6.5, but a limiting magnitude which is close to the average limiting magnitude of his network. And what I've implemented is just that. So now you have the chance in MeteorFlux to change the reference limiting magnitude. Default is 6.5, but usually our video observations, they are of like 3rd to 4th magnitude. And this is what I have depicted down here. So if I use the default, I normalize everything to 6.5 limiting magnitude and then play with the population index. The upper graph is a population index of R2.5, the lower graph 2.0. There's a big difference. So because we are extrapolating to such a large distance to 6.5 max, we get in huge errors. Whereas on the other hand, if I choose 3.5 as limiting, as my reference limiting magnitude, then you see if I adjust the population index, the change is much smaller. So the advantage of this is that the input or the impact of the population index is getting much smaller if you do this. All right, second to last thing. So far in MeteorFlux, you could only separately calculate the flux profile and the population index profile. And now what I have done, you can click a little checkbox in the user interface, and it will automatically generate like put a spline on your population index and apply it directly to the flux density. So this is a comparison. The red graph is a standard with a fixed population index 2.2, and the blue one is really applying the population index that is observed from the data. So this is a new feature that you can use now with MeteorFlux, not just calculating them in separate, but applying it directly. And my very last slide, unfortunately, something which I did not manage to finish for the IMC. I was working hard, I didn't manage. So far, one of our problems is that the IMO network is mostly focused on Europe. So most of the data that we have in MeteorFlux come from Europe. So we have usually these gaps in our flux density graphs because we have just the European nighttime hours. For the America, we have nothing. But we have our All-Sky 7 network. We have almost 1,500 single cameras worldwide. And what I'm trying to achieve is to get also flux density data from these kind of cameras and load them into MeteorFlux. So I have some good progress. This is here a first result I obtained earlier this week for one of my All-Sky 7 cameras. It shows over the course of one night the limiting magnitude for different showers. And I have also the collection area for the showers. The last thing which is missing is really to combine it with the meteor detection. I would say I am done at about 75%. And I hope that by the end of the year, we can also load data from All-Sky 7 cameras into MeteorFlux. And that's it. Thanks, Sirko.
Thank you very much. Ongoing work indeed. Questions? Tom?
I have a small technical question. So to create your spectra, did you use a simple FFT or a spectrum estimation algorithm?
Simple FFT.
It
would ordinary FFT.
I think it would be better to use a really estimation algorithm, because the simple FFT assumes that your data is circular, so that you have infinite copies of your input, and this is definitely not the case, of course, with these counts. Yeah. So that you could try to improve that a bit.
Thanks for the remark.
Okay, more? Yes.
Okay, if I understood it well, for your simulation you used the constant background flux and superimposed with the periodic variation, but the showers like Leonid's 99 shows a very huge change of activity during the observation. So could it make some difference?
It could make some difference. What we have seen in the analysis like 20 years ago was that over the full interval of the one and a half hour where the Leonids were at maximum, we saw these oscillations in the full time frame. So by expectation is it was not really like in the 5 or 10 minutes during the peak, but really over the extended period of one and a half hour where we have this oscillating signal. And for this reason, in my simulation, I also used like the full bin. I did 20, 30, 50 more slides. I just picked up the selection. I tried everything without the background, with more background, played with it. The main outcome was now it's working stable. The input signal that I give with some constant background, with some oscillated additional component really is nicely visible in the spectrum. And that was the main idea of this exercise.
There's nothing in the Zoom, but I have a last one. What would be the physical reason for these oscillations?
Same question as last year, same answer as last year. I don't know. I'm really just a guy who is collecting the observations and who is maybe pointing there is something, and I leave it to our theorists to come up with some clever idea what could be the reason for that.
Okay, to be continued. Thank you. Thanks again.